Welcome to the third episode in a series for calculating pi on my relay computer. And here's where we've got to so far. And it started with a challenge. Simple enough, calculate pi. But this is referring to my computer made of relays. And this thing is pretty limited in modern terms. A mechanical 8-bit computer with the most basic of arithmetic and logic functions. Which means calculating pi, let alone to 20 decimals, isn't going to be a quick or easy task. But then, that's the fun of the journey, isn't it? And so far on that journey, we've taken a closer look at the value of pi, and declared this will be the goal of the challenge, the precision of pi we're looking to achieve. We also settled on the binary-friendly infinite series to calculate pi, the Borwein-Plouffe formula, or BBP for short. This approach is nice because for every iteration you get one extra digit of pi, which means we can stop as soon as we hit our target. Tiny issue though. The BBP formula produces a result in base 16, and so even if things go well, it'll be pi in hexadecimal that my computer produces, and not decimal. That's not insurmountable though, and last episode I covered an approach for converting between bases and used it to prove that the value of pi at the bottom can be derived from the hex above. In other words, if I see the hex value coming out of the relay computer, I know I've got my pi. So, what's next in this episode? Well, it's time to start tackling the BBP formula itself and work out how to implement this on my relay computer. I said earlier that BBP is quite binary friendly, but why is that? Well, it's because it's littered with powers of 2, and having powers of 2 hints we might be able to pull some binary tricks. As we saw last time, we can simplify multiplication in powers of 2 by performing bitwise left shifts, where the first shift will double a number, a second shift multiplies it by 4, a third multiplies it by 8, and so on. Does this help us calculate pi on my relay computer? Maybe, maybe not, but it gives us options, and that's the point. For example, see here? For every iteration, we could increment the value of k and then shift a copy of it left 3 times to get 8 times k. Alternatively, you could instead just add 8 to a value in memory every iteration to arrive at your 8k. And programming at this level is all about working out what's most optimal within the architectural constraints that you have. Another good example is here. Division is a trickier operation, but when it's a power of 2, it's likely much quicker to right shift the value. 4 times in this case, which divides it by 2, 4, 8, and then 16 at each shift. Not that my relay computer has a right shift function, but you get the idea. Anyhow, when tackling a programming challenge like this, it often helps to break the problem down a bit and write some high-level pseudocode to get a feel for the overall logic before digging into the detail. So with that in mind, what does a formula tell us to do? Well, we know there's an iterative part here where we're summing up a result. We also know that the BBP formula produces one hexadecimal digit of pi for each iteration. Therefore, we know that to produce this, it's going to take 18 iterations. So to begin with, our pseudocode looks like this. Looking at the next part, we need to divide the subresult in the brackets by 16 to the power of k. K starts at 0, so this will be divided by 1 on the first iteration, then a divide by 16 on the second iteration, then 256, then 4096, and so on. Now that probably sounds like big numbers quite quickly, but as we saw earlier, an easier way to look at this is that it's a right shift of 4 times k. So nothing in the first iteration, then shift right 4, then 8, then 12. Effectively, we're placing the subresult further and further down the binary fractional part. Let's add that to the pseudocode. So here v will be the value from the formula in the brackets, and vs will be that value shifted 4k times. That is, v divided by 16 to the power of k. Finally then, we've got the formula in the brackets here. And that's 4 separate divisions, although they all have the 8 times k in common. So let's pick that out first and call it dv. And then I'll name the 4 divisions a, b, c, and d respectively, and then the total of the formula in the brackets is a minus b minus c minus d, giving our subresult of v. So there's our high-level program, and at the moment it's not looking too complicated. Certainly no more so than the BBP formula itself. The next logical step in my mind is to try and implement this in a modern computer language, just as I did last episode with the decimal binary conversions. My reasoning for this is that it proves out the formula and my high-level pseudocode, but also gives me a chance to see how the results build up over time. Having that understanding will be critical when it comes to tackling this on the relay computer. So here we are again, back in Visual Studio Code with some C# ready to go. This builds upon the code shown in the last episode, and if you'd like to take a closer look, it's available on my GitHub repo, link in the description below. It's here in part C where the main action takes place this time, with part A from last time being the decimal to binary conversion, and part B, its reverse, the binary to decimal conversion. We'll use parts A and B later to verify the calculated value of pi, but for now let's take a closer look at the calculate method in part C. A key thing to remember is that my relay computer infers no meaning on the values held in its memory. Everything is just ones and zeros grouped together into 8-bit blocks. Therefore, if we want to treat a value in memory as a signed integer, we have to do all the legwork to handle that. The same is true for fixed point binary numbers. It'll only act as one if we program it as one. True for an 8-bit value, but even truer for a value requiring more than 8 bits. At that point, we as the programmer have to closely manage each byte of our bigger value. Here, we use a .NET big integer, which for our purposes we can effectively think of as a contiguous array of bits, and we have to carefully track where the bits of the integral part sit and where the remaining fractional bits sit. Here we're allowing for 4 bits for the integral part, and then the precision passed in here is the number of bits that the fractional part should be calculated to. Our sum variable then is notionally treated like this in memory. But it's important to remember .NET will just treat it like a very big number, and all arithmetic and logic operations will follow suit. And this is good training for how we'll need to handle the sum on the relay computer. In this picture, as we add more bits of precision to the right above, so 2 to the power of -12, -13 and so on, we have to add additional bits to the left of our fractional part, so 2 to the power of 11, 12, 13 and so on. But note it's always the most significant bit where our fractional part starts in either case. In the picture here then, we're using a precision of 11, because we have 11 bits after the binary point. But if we look back up here, we actually call our routine with a precision of 17 plus 2 times 4. Well, each hexadecimal digit takes up 4 bits, and we want 17 hex digits after the binary point, hence 17 times 4. The plus 2 I'll explain in a moment, but have a think and see if you can spot why. And no, there's more to it than the comments in my code make out. Right, back to our routine, and let's bring up the pseudocode from earlier to follow along. We need to perform 18 iterations of the sum, so we set our k loop up here, and then set up our value dv to be 8 times the current value of k. Next, we calculate out our 4 divisions, a, b, c and d, and what maybe looks a little odd here is the left shifts. Well, that's because we can't just start with a value of 4, 2 or 1. That would be right down the right end of our big integer and represent a tiny fractional amount. We need to shift it left by the current number of fractional bits to get that value into the integral part. Now from .NET's perspective, it looks like we're creating a very large number, but it's all because of how we're interpreting that big integer as a programmer. With the shifts done, we'd now have a 4, 2 or 1 in the integral part of our value. Note though that we don't shift the divisor, that stays as is. Now admittedly, this seemed counterintuitive for me for a while, but remember that this will be integer division and so we need our divisor scaled down. It's the difference between say 1,000,000 divided by 6 and 1,000,000 divided by 600,000. We won't see anything after the decimal point, so our first result is 16,666. Our second result is 1. Out of interest, how big do you think our big integers are going to be? Well, how about this? This is one of the intermediary hex results that we'll be dealing with, and its decimal equivalent, deep breath, is 237 sextillion, 372 quintillion,
28 quadrillion, 988 trillion, 26 billion, 763 million, 254,887.
Big. And all that, divided by 6, is this equally sizable number. And this time we only lose 0.5 in the division. Now, if we imagine the decimal point to be right after the 39 sextillion mark, then you can see how we've kept all that precision within an integer. And that's exactly how we'll achieve our precision of pi. Losing that 0.5 here also reminds us why we need to calculate pi to extra precision, because that number should end in 815 when rounded rather than 814, and gradually that error will accumulate. But if we strip off, say, the last two digits at the end of the calculation, then the error accumulated would have no effect. Right, enough of that, back to the code. Next, we subtract b, c and d from a to get our sub-result v, and then we right shift 4k times to put the result in its correct place in the fractional part. Effectively, this means that at each iteration the sub-result is placed another 4 bits further down the fractional part. This is also why we say the BBP formula outputs one hex digit of pi at a time, because at each iteration another 4 bits of the result won't be impacted by adding the sub-result, because of our right shifts. Finally then, after some outputting of the values, we add our sub-result to the overall result and we're ready for the next iteration. At the end, we split up our big integer into its integral and fractional parts and place those in the same custom type I showed last episode. As before, we can use the same masking and shifting tricks to pick off each part. OK, enough code. Let's give the thing a run and see what it produces. So let's look at the first iteration where k is 0. The first 4 lines are the divisions which on this iteration are 4 divided by 1, 2 divided by 4, 1 divided by 5 and finally 1 divided by 6. See how the 4 in the first line occupies the first 4 bits of the value, the integral part. There's an imaginary binary point right after the 4th bit where the fractional part starts. You can see this on the second line. 2 divided by 4 is 0.5, a half. We see that the 5th bit from the left is set, representing a half. The bit after that is a quarter, then an eighth, and so on. What's more interesting though is the value of 1/5 and 1/6 on lines 3 and 4. Notice how these have a recurring pattern of bits, and that's because binary can't represent these values exactly, and the more bits we have available, the closer we get to our value, but would never fully reach it. Again, this is where the precision becomes important, and any truncation in these individual values can build up when we start summing things up. Having that extra precision ensures we have enough bits to get an accurate value. If we use less bits, or rather exactly the bits needed to fit our desired value of pi, we'd actually find the last hex digit would be incorrect. If we now look at the next iteration with k equal to 1, we see again our 4 divisions, which we then combine with a first minus a second, third and fourth to get our intermediate result. This time we right shift by 4 bits and add that to our result so far. We're now 2 iterations in, and therefore our first 2 hex digits of 3 and 2 are locked in and won't change. This repeats and repeats, so let's head down towards the end at k equals 16 and 17. By this point, we're right shifting so far that at k equals 16 we only get 2 bits of the intermediate result, and at k equals 17 we lose the whole lot. That means that specifically for this calculation we can drop the last iteration. It makes no difference to our outcome, and you can see the sum is identical at k equals 16 and 17. Let's make that change and rerun now. That's better. So what's the outcome? Here's the value of pi we calculated, and if we truncate it to 17 binary places, we get our expected value, and it matches the known value of pi that we converted to hexadecimal in part A last episode. To close things out, we convert our calculated result to decimal and convert that the value of pi is indeed the value we started with. Just before I leave this, and to prove I'm not making stuff up, let's drop the precision on the pi calculation and see what happens. And here you can see that the last 2 digits of pi are incorrect, because when adding up we didn't have enough bits, so there was nothing to bump the last 2 digits up. Anyhow, this is all good news so far, and with this programme, not only do we know the formula works, not that I doubted Bailey, Borwein or Plouffe for a second, but we can also see some intermediate results, which will be crucial for debugging our relay computer programme. And speaking of which, where do we go next with all of this? Well, let's revisit our pseudocode again. And I've updated the K loop to run from 0 to 16, following what we found just now in the .NET code. Right, I think there's 2 things we'll need to consider next to get from the BBP formula to my relay computer. Firstly, our pseudocode has quite a few variables, so we'll need to think about how and where to hold them, how big the values need to be, and what type of variables they will be. Secondly, we need to look at the types of operations going on in the pseudocode. Effectively out of that, we'll get a shopping list of operations that we need to implement. And that's where the real work starts. If we're lucky, the items on our shopping list might be something the relay computer can do natively, but it's far more likely to be something we'll have to piece together. Anyhow, that's all for next time, but so far I think things are shaping up nicely, and we've proven out the BBP formula and observed how it behaves and builds up the result. As I mentioned at the beginning of this series, I'm kind of learning and working things out as I go, and even now can't say for sure this challenge will end in success. But I am getting more and more confident as we go. The next big hurdle is ticking off that shopping list, by which point I'll be surer than ever that it's theoretically possible for my relay computer to run this programme, and maybe then it'll just come down to, can my computer run reliably enough for long enough to complete the calculation. Anyhow, perhaps rather foolishly, that outcome doesn't deter me, and I'll keep taking steps in that general direction and see where the path takes us. For now though, thank you for watching, and I'll see you next time.